next speaker is Gaia Grosso, who's originally from beautiful Padua, but now comes to us from a mixture of Harvard and MIT, NSF Institute I-Phi, and she's talking about high dimensions, the statistical discovery, anomaly detection at scale in the era of latent spaces.
Thank you, Larry, for the introduction. And first of thanks for inviting me today. It's really great to be here. And it's really, really cool to see all this merging of different topics in the same, let's say, common tools. And so I guess my talk is a bit off like the SBI only, let's say, topic. It's going to be about anomaly detection. There's going to be a bit of SBI sort of in it. But I'm going to try to sort of solve it or answer the questions or propose ways we can address the question of how to scale up anomaly detection to like realistic scenario, realistic problems. In particular, these days, thanks to the developments of new AI models and new AI tools that allows us to take advantage of very rich and powerful data representations. And I want to first start, I don't know if I did it right, by acknowledging the people that sort of contributed to the things I'm going to talk about today, in particular the two groups I'm part of. As Larry just mentioned, I'm part of this NSF AI Institute that is in between AI and physics. So I work with a group in Harvard and a group in MIT in like AI and physics respectively. And so I wanted to just take a moment to acknowledge their contributions and also the contribution of collaborators from ETH, in particular the students, Kyle and Jada, that worked with us during this couple of years. And so throughout this talk, I'm going to essentially touch on three main topics. I'm going to talk about modeling assumptions and how prior knowledge and inductive bias shape essentially detection powers and detection tools for anomalies. I'm going to talk about interpretability. I know this is a very fuzzy, let's say, concept. So let's say in better words, I'm going to talk about how we can extract intelligible knowledge out of anomaly detection tools and how that could help us characterize what anomalies that we find is. And I'm going to talk about applications that are going to go even beyond just the scientific settings that is the setting where I come from. And by going through these topics, I'm going to sort of try to address two themes or two topics that I've been working on in this past 2 years. And essentially, the first one is going to be how to exploit background knowledge to build smart representations for our data for anomaly detections. And the second topic or themes is going to be how to choose a good set of inductive biases for model test design for anomaly detections, both for enhancing sensitivity and interpretability. When interpretability needs this. And even before starting with giving you a sort of an introduction of what I've been doing, I want to sort of phrase the problem. So what I'm doing when I say I'm doing anomaly detection is essentially a statistical approach to anomaly detections that is essentially defined in the following way. So let's say we have a data set, so a collection of data that are independent and they live in some RD, so where D is to be specified, and we have a understood notion of a normal behavior, that is our null hypothesis, and we assume we don't have any knowledge about what the anomaly is or what the signal is, then the question we are trying to answer is there any statistical evidence of anomalous behavior in our data? And why do we care about this question? Well, there are a bunch of interesting applications, both in science and beyond science. I'm going to just show you a bunch of examples from the scientific domains, but they're essentially covering the topics of validations, monitoring, and discovery. So we can think of, for instance, one of the applications being trying to validate a new surrogate model. We have seen many applications during these days about SBI to produce surrogate models. Another application would be just monitoring. So let's say we have an experimental setup and we're looking at some summary statistics and we want to see whether a change in environmental conditions or a controlled change in our experiments affect our summary statistics. And we kind of solve these questions. And ultimately, but last but not least, discovery. So we have some theory laws about physics, for instance, in our case, but we can just go beyond the physical sciences as well. And we want to check whether our data do agree with our theoretical models or there's something new beyond that. So the way to address this problem in a statistical sense is, well, when we have a tractable model for our null hypothesis, essentially building a goodness of fit test, where essentially we build a map from our data to a scalar, and this map sort of is aware of the information about our null hypothesis. We build a distribution for this test statistics under anomaly-free conditions, so in our null hypothesis essentially assumption, and then we compare the observation for the test in real data or data that we want to expect with this distribution to extract a p-value, like shown here in the cartoon. Of course, most of the time we don't have access to a tractable model for our null hypothesis. We often have instead access to some data that are good representation of this hypothesis. So when we are in these settings, essentially the goodness of fit test translates into a two-sample test where the matrix of similarity is essentially built between two samples rather than a sample and a theoretical model. The approach I'm going to talk about today, or I'm going to study in today's talk, is a normal Pearson hypothesis test or two-sample test that essentially you can see as a goodness of fit test, but also in practical regimes is essentially a two-sample test. And the idea is that starting from the classical definition of a normal, curation normal Pearson test, and release our assumptions on the alternative model by parameterizing it by means of some machine learning models, as you can see here. And we've seen, in a few, let's say, papers from now it's almost 10 years ago, I would say it's 8 years ago, 2018-19, is that we can sort of translate this problem of maximum likelihood into the minimization of a loss function, and the loss function will essentially take this form over here, and essentially is as solving a binary regression task where we are comparing two samples, one that is completely essentially normal, where a golden sample representing our anomaly-free conditions, and the second sample is the data of interest that will have some usually small fraction of anomalies in it, and we want to try to detect that. So it's not that very different from what we've been heard during this couple of days about the ratio trick and this how it works. But so the question is okay, we have done a bunch of papers along the lines of these methods that essentially show that we can use this in multivariate setups, we can incorporate uncertainties in it, and we can also obtain some sort of state-of-the-art performances in terms of sensitivity, and this is very cool. And we also sort of realize that inductive biases that are essentially present in the choice of the family of machine learning models or universal approximants that we use for defining this parameterization sort of matter in terms of identify the landscape of the sensitivity and the power of the test that we define this way. So we have a lot of results that show that this method is promising, but then the question is, how do we make this work in realistic settings? And where essentially, I guess I don't have to convince you, but we live in a world that is very complex, where our data, both from experimental, let's say, physical science experiments or everyday life, are very complex, and the complexity of the data is essentially growing the more we build better sensor and better data acquisition systems. So how do we get a p-value out of such a raw complex set of data and observations? Well, we always have to undergo some level of summarizations, and doing this kind of summarization requires making some assumptions. So there is no free lunch for anomaly detection as well. And so the question, and so the let's say standard way to address this problem is that we make assumptions at essentially two stages of the data analysis pipeline. That is the feature extractor. So there is a first stage in which we decide which observable to look at, and then at the level of the design of the statistical test we perform. And so the question is, how do we do this kind of, or how do we make this kind of assumption, which assumption we should make when the kind of signal we are looking for and the power, the sensitivity power should be tailored for anomaly detection, and we don't know what anomalous means. So I'm going to talk about essentially ideas or things we've tried in order to address these two problems. And I'll start by addressing or like talking about ways one can build some smart data representations for anomaly detection using background knowledge, so knowledge about the processes or the physical process or in general processes in our observed data that we are aware of. And the way we did that is by essentially studying and trying to use a method for essentially building data representation that is called supervised contrastive learning. And the idea is essentially to take our data. This is a cartoon with cats and dogs, but to sort of explain the idea better, essentially we build pairs of data from our set of data points that we want to arrange in the representation space. We embed them in this representation, and we govern the dynamic of an organization of these data points in this space by essentially building some push and pull, so attraction and repulsion dynamics based on similarity between these data points. And so what happens is that we can build positive pairs, so pairs of data points that we expect or we would like to be close to each other, and negative pairs and pairs that we would like to push apart. And this can be done like in unsupervised or supervised way. In this case, we are looking at supervised ways, so we are using labels to build this pairing. And the hope is that this kind of dynamics of training for an embedder will help us to build some representation space that is structured and help single out the anomaly. So this is a set of results, just to go quick, of like a first experience we did along these lines. It's essentially a test done on data coming from collider experiments. It's essentially, the data set is available online. It's part of this anomaly detection challenge data set is, and here put the reference for the paper that is described. The data set, but essentially these data are collection of data that simulates the level 1 acquisition from a CMS experiment. And essentially, for people that are not expert in this field, this means like we have 19 objects that are essentially particles in particle physics settings. And for each of them, we have sort of three variables, three observables that essentially define the three momenta of these objects. So in the end, we start with an initial representation that is 57 dimensional, so it's not huge, but still very large for addressing problem of like density estimation with usually not like billions, like not necessarily a lot of data available for training. And we are given like 4 classes in this data set. So these main background classes and that populates this data taking settings. Is in particular a trigger that essentially selects events with leptons. So that's why these are like the main process, but it's not really that important for the point of the method. The point is like we are using these 4 classes or 4 labels to do the pre-training of a data representation space that is as small as 4-dimensional. And what we do is that we perform this normal Pearson test on top of this 4-dimensional representation. And we compare it with the alternatives. And so on the right side here of the slide, you see 4 panels. The first one on top, and this is test statistics, where the purple is the distribution of the test statistics under the null hypothesis, and the green one is the distribution of the test statistic when like a signal is injected. In particular, we are looking at a black box here, so the signal is not even sure what it is because it's not been told. And it's coming back. Right, so I keep on talking in time. So the top left one is essentially sensitivity or the result of a test statistic on 57-dimensional space, that is the original one. Then we have on the top right and top left some alternative representations. One comes from some physics inspired essentially reasons. So these are observables that will be chosen with some rationale from physics. And on the bottom left, we have a six-dimensional representation coming from a latent space built on top of a variational encoder. And what you can see is that none of these representation is able to sort of provide results for a test that have a power for discovery, while our test, so combining the normal Pearson test with a good representation of the data, even when this representation is really low dimensional, allows to get to discovery. So we thought this was really, really exciting. And once we saw this result, we were like, okay, can we just bring this result to like a more general settings? Can we just use this somewhere in like a more challenging regimes and with other data sets, with other applications? So, yeah.
Yeah. The entries in this diagram, of course, like it's not per event, it's like a whole data set, right? Like you give it a whole data set and then
right.
you get a number.
Yes. Yeah. So it's each of these entries like one realization. So it's like a toy. Right. And there are multiple for the signal as well, simply because the black box that we've been given was like a million data points, and we divided in 10 chunks. Right. Yeah. It was just like for computational reasons, we wanted to address the problem like with some reasonable amount of time. But yeah, so the like statistics we're using here is like 100,000 data points for like backgrounds, and we know that the amount of signal fraction in this black box, even though we don't know what it is this 1 per mil. So we expect sort of 100 per chunk, but it's not given because we just don't know the labels. So yeah, that's why there are multiple entries there. Yeah. So when we saw all these exciting results, we were like, okay, let's just bring this forward and see where we can apply, or to which extent this generalizes to other problems and other dimensionality, other complexities. So we made a sort of a systematic scan of different scientific, let's say, applications and different initial data modalities, different embedding architectures and stuff like that. And we ended up preparing a paper that has been accepted in NeurIPS this year, that essentially shows that this idea of encoding information about our previous domain knowledge in labels and use this to help either training from scratch or fine-tuning an existing data representations to build a better data representation for anomaly detection is actually working, and is working in many different regimes, and it helps us reaching sensitivities down to the level of percent of per mil in many different applications. Keep on doing this. So this essentially is addressing the first part of the problem itself by providing low dimensional signal agnostic, because all this pre-training has been done just with background knowledge representations for anomaly detection. But of course, not all the times we have labels available. So in particle physics, we are sort of really lucky because we have the ability of simulate as well, and we can build big data set with labels. In other settings that's not necessarily the case. But there are other like modern applications where different, let's say, kind of pre-training, like unsupervised pre-training, help us building a very rich set of features in a task-specific ways. And this feature can be interesting and help to encode data properties in a way that is easier to do anomaly detection on, despite the fact that they're very, very high dimensional. So the question is, well, given that we have these good data representations are either low dimensional and with some like domain knowledge in that, or very high dimensional and specific, is there a good way to test, to design a statistical test for anomaly detection that work in these spaces? And so the point I'm going to try to prove for the rest of the talk is that, yes, we can address this problem by impose the right set of assumptions in the modeling design of a statistical test, still in the normal Pearson settings for now. And let's say assumption I'm going to try to motivate the rest of the talk are essentially sparsity, locality, and competition. And so let's try to motivate that. So first off, what do we want out of this test? What I want out of this test is sensitivity, but also some sort of interpretability. And so I mentioned at the very, very beginning of the talk, for me, interpretability means that I can extract some characterizations or some understanding of what this essentially anomalous score has found. And well, maybe sparsity is something, it's sort of easy to buy, because I mean, when we are looking for anomalies, usually we are in settings where the amount of anomalous data is very, very scarce compared to like the amount of normal data. So we expect data themselves to be like something, essentially that you can capture with sparse degrees of freedom. On the other hand, locality can be motivated with like two main points. On the one hand, the hope is that the like structure, the geometrical structure of this smart latent representation will encode information in such a way that anomalies will clusterize or will emerge as a local behavior, and hopefully what is like close by in the, let's say, observational world, or even the world of like generation or theory models, will be mapped close by in a space that has a rich enough set of features. And the other point for locality is interpretability, and I'll show you later how this property is really, very useful to be able to extract some meaningful information out of the model. And then competition and exploration, they sort of are useful to span the space and being able to localize and find anomalies even when we don't have a good prior assumption on where the signal will appear in our data representation. And that's in particular relevant when we are looking at high dimensional spaces where we really have no clue where the signal will appear. So how do we put this all into the Neumann-Pearson test? Essentially by defining like a modeling for essentially like the parameterization of the alternatives. Well, I can go back, I don't know, this doesn't work, just quickly to the slide of the Neumann-Pearson test. I wanted just to make, to point out again that the parameterization we're doing of this alternative density is by essentially by means of an exponential family. So the F that we are here modeling is modeling the log density ratio. And so when we're making this modeling assumption for F, essentially making the modeling assumption on fitting something that should be flat almost everywhere where signal is not present and should have some structure only where in those regions in spaces where anomalies will emerge. And so the modeling we are doing is this, what I call here Sparker, that is a sparse ensemble of self-organizing local kernels. As local kernels, we're choosing very simply Gaussian kernels. And when I say it's organizing, essentially, I'll explain you better in a minute, but we essentially add this activation function in front of these kernels that has a competitive feature, essentially. And it's essentially almost like a softmax activation. And the sparsity comes from the fact that we're imposing M, so the number of the features we assemble over, to be very, very small compared to the number of training points. And when I say small, it means like really a handful. And examples I'm showing you later in the talk are going to be on application where the number of kernels I'm using is like 5, and the dimensionality of the problem is like 1,000. So this is kind of like this kind of sparsity. And so yeah, look, locality, as I said before, helps interpretability because essentially it pairs the activation of the anomaly score to a specific location in a space. So essentially giving me an information about the geometry of the activation, and that's helping to identify the regions of the space that are anomalous. And this is something that you cannot do with a layer like a ReLU, with a ReLU activation, because you cannot really pair activations with a specific location. So that's the power of local, let's say, activations. And competitions, as I said earlier, it helps interpretability because in some way, it forces these degrees of freedom to self-organize in a way that they specialize and they become orthogonal to each other. And this is helpful for disentangling and better understanding, better interpreting the activity of the model, but at the same time, it helps efficiently explore the space because these kernels will all try to explore different regions of the space, optimizing the chance of exploration. The other interesting feature about this model is like the scale. When we define a Gaussian kernel, we have to define a width, and this is a parameter that affects the sensitivity a lot. And so what we are doing is that we are annealing over this parameter. So we start from very, very blurred and highly activated models that are not very informative, but they are like sensitive and aware of the whole space. And we gradually reduce the width by making model more and more narrowed and specialized to locations that eventually will turn out to be anomalous. And this both give us robustness and better interpretability. Robustness because we are essentially performing a test over multiple widths all over one single machine learning training, essentially. And we are going to use them all. So I don't have a lot of time, so I'm just going to jump to conclusions or like results out of this, and results that are making me excited about this model and making me study it further. And so here I show essentially a set of sensitivity or power of the model across different domains of applications, so different applications in science and also out of the scientific domain where the dimensionality of the data representation is different. It goes from very, very low, like 4 dimensions, all the way through 1,000 dimensions. The signal injection is over or the order of some percent. And I compare here the performances of the Sparker model used for the NP test, the Neumann-Pearson test, with a previous version of the Neumann-Pearson test based on kernel methods, where we have essentially, again, flexibility to learn some distributions and adapt to the space, but we are using order square root of n kernels. And the right side here, MMD, is, Larry mentioned it quickly earlier, it's a test for, a 2-sample test that doesn't require any sort of training. It embeds essentially points to a kernel embedding. And again, it requires at least a square root of n. In this case, we are doing this Nystrom approximation where square root of n kernels is enough for reasonable performances. Both of these baselines are affected by the choice of the kernel width. Okay, yeah. And here we are sort of taking care of that by making a multiple test over kernel width, which means for MMD doing the MMD version called MMD agreg, or is something that you can find online. And for this is essentially taking the minimum p-value across different choices of kernels width, so that the essentially comparison is fair. In Sparker, because we anneal across different kernel width, and we have access to a model for each value of the width, we also are doing some multiple tests over kernels width that we touch in the annealing. So all of these approaches are sort of robust against scale. These are other exciting results. So, okay, first, I didn't say it here explicitly, but maybe you can see it already. Sensitivity with our model are either better or comparable with existing approaches. So this is super cool, in particular when we are addressing problems that live in high dimensions. And yeah, the other very interesting point that is maybe the one that excites me even the most is the fact that we can extract some information about the anomalous score that is interpretable or gives me information about the geometry of the anomalies. So here on the bottom, I show one of the applications we had that is based on language, essentially. It's a little toy model where we asked an LLM to generate lines from the Dante Divine Comedy, and we inject this like AI intrusions into some ground truth lines of the Divine Comedy and check whether the model was able to identify this. The representation is a really funny experiment, but actually it's it's representative of some application in real life where we are these days using essentially AI to generate language. And I bet we want to know whether we are talking to a real human or with a bot or things like that. So we embed all this data down to with a sentence transformers into this 384-dimensional space. And what you can see is that if you just do a easy do the PCA projection, all these anomalous intrusions are in distribution. So it's very hard to think of like a classic way of just like finding like a good cut in this data representation space to highlight the anomalies. While if you have sort of a Norman Pearson kind of task together coupled with the sparsity and locality assumptions we are making, we can sort of identify some specific directions in space or features that highly activate for the anomalous points, and here in the space, for instance, and we can look at them and look at like essentially the points that activates the model the most, and see that there is some pattern in the activation of the different kernels. And this tells us essentially there are specific locations in this 384-dimensional space that is worth investigating and further monitoring. And that's really nice. And we can do, and I will go very quickly now, but we've done something similar for open world novelty detection with images, where the embedding is 1,000-dimensional. And again, for physics data, this is an example from jet data from LHC experiments, where we are looking for essentially what we have decided to be anomalous data, that in this case is a Higgs decay, boosted Higgs jets, essentially. And what I wanted to just quickly point out here is that you can further, let's say, exploit information that comes from the activations of these kernel features by correlate them with existing observables or physics-inspired observables, and tell whether there's any correlation or interesting features to pick. In this case, we essentially correlate the most activated feature here with the mass of the jet, and we kind of see the resonance of the, let's say, Higgs signal being identified. So this brings me to conclusions or concluding thoughts. I saw now this quote, not from anyone famous, and no, but we had this this workshop famous enough in this community, So we had this workshop in Munich like last month about building big versus building smart, and I thought this was exactly the essentially right title for the closing thoughts about my talk today, because essentially I'm exploiting both large models and smart models to find anomalies. And in the first place, large models give us a very rich representation of our data that can encode many properties, also unspecific or like task-specific properties, and then we can use this huge rich representation to better characterize our data and perform anomaly detection on top of it with smart model. So models are small and they have some controlling set of inductive biases that help us to characterize and identify the anomalies. And what makes me excited about this, of course, is that we are reaching very sensitive performances for scientific applications, and it sort of opens a way to so many different problems and application in science, but also it gives us a tool to inspect these big models that the AI folk are building, and trying to understand better what's inside there, and can we build them more robust, or can we understand what's going on behind it. And I added this slide after our dinner yesterday, after a comment with Kyle, and it's like pointing out a bit more this essentially topic about inductive biases in anomaly detection. And I think I just wanted to mention it's a kind of like remark once again that when we do anomaly detection, we're not really just doing a completely uncontrolled detect of our data. There is always like an amount of domain, like information and assumption you had to include in your modeling. And sometimes this sort of inductive biases, either you're doing them implicitly or explicitly, or you're aware of them or not, they can become relevant. And I think they become very relevant when you're in regimes. I just realized there is a thing here that moved, but when you're in regimes of your, let's say, landscape of anomaly detection problems that are very close to like nothing or very small amount of anomalous signal, anomalous points, and in order to fit something over there, because you have lack of information coming from data and evidence, assumptions will take over and become very significant in shaping the power of your test. So even in particular, when we are in these settings, being aware of the inductive bias we are enforcing our model and controlling them becomes relevant. And I think I'll stop here. I just wanted to make a quick comment on what's next. And for me, I think what's relevant to look into right now is how to cope essentially these rich presentations with safe, like robustness and domain shift, and how to quantify uncertainties, put together our let's say existing tools in SPI with tools for controlling domain shifts, and build robust models and robust statistical tests out of it. And that's it.